Previously, we used the Mayer-Vietoris sequence to compute the cohomology groups of the circle. Now we will go up one level. We'll compute the cohomology groups of the product of the circle with itself, i.e. the cohomology groups of the torus. Now, since the torus is connected, we know H0 must be isomorphic to R. And since it has dimension 2, we know that the cohomology in degree bigger than 2 must all vanish. So now it remains to compute the H1 and H2. To use the Mayer-Vietoris sequence, we need a covering. So let's cover M by this two open set U and V. And here I'm assuming they're actually intersecting, but I couldn't draw that. So let's say they're actually intersecting, and you see, so they will intersect along these sleeves here, right? So this is their intersection. So why do we choose U and V this way? Well, because observe that U and V are just homotopic to cylinder, and thus homotopic to each of them homotopic to the circle. Even U intersect with V here can be expressed in terms of circle. Look, this is just 2 circle. That's really convenient because we just computed the cohomology groups of the circle. So now we can put that fresh knowledge to good use. We can fill in all of these. First, observe that their circle has dimension 1, so H2 is 0, so all of these is just 0. Now the circle is connected, so the H0 is just R. And then this intersection has 2 connected components, so this is just R squared. As we have computed before, H1 of the circle is also just R. Look, the sequence is almost all filled in already. Alright, so now let's find H1 and H2 of the torus. Now observe that because this is surjective by exactness here, right? H2M is image of D1 star. But then, by first isomorphism theorem, that is just the quotient of H1 of U intersect with V, quotient out by the kernel of D1 star. Now by exactness here, we know that the kernel of D1 star is equal to the image of J1 star. Thus, we just need to understand what this map is. So let us review the definition of this difference map. If omega is a one-form on U and tau is a one-form on V, then this difference map just sends this omega comma tau to the difference between tau restricted to U intersect with V and omega restricted to U intersect with V. So what are these forms? Well, there's just gonna be pullback of omega and tau under the following inclusion maps. So we have an inclusion map from U intersect with V into V, right? And we also have an inclusion map from U intersect with V into U. The restriction of this one form tau to U intersect with V is just the pullback of tau under this inclusion map, right? That would result in a one form on U intersect with V. And similarly, the restriction of omega to U intersect with V is just the pullback of omega along this inclusion map. Alright, so that's the definition of this map, but that's not yet useful for our computation. Now we want to give an explicit description of this map when we identify these cohomology group with copies of R. And I should have mentioned here what these A and B are. So when we take the intersection of this U and V, this intersection, I will call this part A, right? And then this part is B. They are H homotopy equivalent to the circle, so their H1 is just isomorphic to R. This intersection is just the union of this A with this B. So to understand what this map is, we want to compose it with these injection and these projections. Now the key idea here is that A and B, each of them are deformation retract of U and also of V. Thus we see that this map must be an isomorphism, this map must be an isomorphism, this map must be an isomorphism, and this map must be an isomorphism. So all these 4 maps. Now if we identify each of these cohomology group with R, then we can find explicit formula for this map as follows. So let's say we start with some point AB here, right? Okay, so let's see what it should map to. What is this B restricted to U intersect with V? So what is the image of this B in H1 of U intersect with V? Well, that should correspond to a pair, right? One correspond to image of B here and one correspond to image of B here. But we've said that these two maps are isomorphism. So this really is just B comma B. And similarly, we'll see that the pullback of A, right, under this map, it's gonna be A comma A. So this map J1 just sends A comma B to B minus A comma B minus A. In particular, its image is the diagonal. Thus coming back, now we can compute the second cohomology group of M, right? It's gonna be the quotient of R squared over the diagonal. And that's gonna be isomorphic to R. Thus we get that this is R. Alright, so we have nailed down H2. Now only H1 remains. One way to figure this out is by computing dimension, because by using rank nullity we can see that the alternating sum of dimensions of everything in this sequence must be 0, and we know all the terms in this sequence except for H1. So we will be able to deduce that the dimension of H1 must be equal to 2, and thus H1 must be isomorphic to R squared. So that's one way, using the alternating sum of dimension. Now another way is by explicitly tracing this sequence. So let's do that just for practice. Okay, first, by the first isomorphism theorem, we know that this H1M must be isomorphic to the direct sum of the kernel of this map, right, with the image of this map. Okay, but then by exactness here, we know that this kernel, if this map is gonna be isomorphic to image of this D0, right, and the image of this map is isomorphic to the kernel of this J1. And we mentioned that this J1 map just takes the difference of the coefficient, right? So its kernel is just the diagonal and thus isomorphic to R. Alright, so now let's look at this component. So what's the image of this D0? Now by the first isomorphism theorem again, that's gonna be isomorphic to this H0 of U intersect with V, quotient now by the kernel of D0. But by exactness here, the kernel of D0 is just equal to the image of this J0, right? But again, this map J0 here is given by exactly the same formula as J1. So the image of J0 is gonna be the diagonal, and thus this quotient, right, it's gonna be isomorphic to R. So then H1 of M is gonna be isomorphic to 2 copies of R. Alright, so that's how we can use the Mayer-Vietoris sequence to compute the cohomology groups of the torus.